So dropout is seemingly a very simple concept. It's as simple as randomly dropping some of the connections while training the model. And this leads to regularization of the network. Now, if you're familiar with the typical or traditional regularization techniques such as L1 and L2, connecting this technique with regularization may not be clear. But it is indeed a regularization technique, and this was shown by Pierre and Peter in their paper. I think the paper was in 2015, and there they showed that this dropout is actually under, so they showed that under some simplified assumptions such as linear activation, dropout becomes equivalent to applying an L2 regularization on the network. And I'm gonna show the expression that they arrived at for the loss function of a network under dropout in presence of a dropout layer. So this was the expression derived by Pierre and Peter, and it was actually in their paper in 2013 or 2015. The paper was Understanding Dropouts. In that paper, that they showed that under linearity assumptions, the loss function of their network becomes of this form when we apply dropout. Here, the important part we have to look at is this, actually this entire term. Here, P is the dropout rate. Basically, if P is equal to 0.5, as I had set it here, P as 0.5, then you drop 50% of the connections. So P is a hyperparameter for the dropout. Now, if you look at this expression, this is a standard least squares term, and this is the regularization term. If you look closely, this is regularization term because these WIs are the weight parameters that you want to estimate. Outside of this least square term, there is this additional penalty term, which is penalizing the values of your weight parameter. Meaning, if you have a lot of these, if you have all of these connections on, this loss is penalized. This loss is forcing you to make some of your weights closer to zero, because that will benefit the loss. It will make it smaller. And that's how a regularization term works. It penalizes the presence of your weight parameters. It pushes you, or it pushes the model to make those weights closer to zero. And so this is a regularization term, and here, let me use another color now. This P times 1 minus P is the penalty parameter. Basically, if you compare this with the traditional L2 regularization expression, which looks something like your least squares function, let me use the expression that is very commonly used in regression, and I will replace beta with W to have the same terms. Here, lambda is the penalty parameter, same as P times 1 minus P we have here. And just like in this expression, you increase lambda to increase the regularization. Similarly, here you want to increase this term p times 1 minus p to increase or maximize your regularization. But because p can take value only between 0 to 1, it's a fraction between 0 to 1. So the maximum value that p times 1 minus p can take is when p is equal to 0.5, in which case this is actually 0.25. That's the maximum value it can take. If you increase the p, it will reduce. If you reduce the p, it will reduce. Basically, it's of this shape, where when p is equal to 0.5, you get the maximum. So in short, under these linearity assumptions, Pierre and Peter showed that first, dropout introduces a regularization term in the loss function of our deep learning network. And second, that the regularization is maximized when we set the dropout rate equal to 0.5. These are two very important learnings from their work. Although their work was derived based on linearity assumptions, they also extend to nonlinear, the typical nonlinear models that we have. The takeaway from here, from implementation point of view, is whenever we have to add a dropout layer, we should set our dropout rate equal to 0.5. We should use it as a default. We should not put much thought around it. If we think that a dropout rate of 0.5 is deteriorating the model, making it perform worse, then instead of changing this, you wanna increase layer size. This is a better approach than reducing your dropout rate. Why? Because when you increase the layer size, now you're trying a larger model, and with larger model, you get overfitting issues which you are resolving with your dropout regularization anyway. So use p equal to 0.5, but remember another thing. You should use p equal to 0.5 only for your intermediate hidden layers. Do not use it for input layer. Although sometimes people suggest we can use dropout on the input layer and keep the dropout rate small, like p equal to 0.2. And this means we are randomly dropping 20% of the input features. This would work similar to how some machine learning methods like random forest works, in which we arbitrarily drop some of the features while learning. But this is not necessary in deep learning models, especially when you are building your first baseline models. And determining what would work best for the input layer is also not straightforward, therefore this is best avoided. As a rule of thumb, it is good to not put any dropout on the input layer, put it on your intermediate layer with the max possible regularization that you can bring by putting p, your dropout rate, as 0.5.